Hello viewers, welcome to CEC-UGC online lecture. In today's lecture, we shall be discussing the mechanism of SN1 reactions. As you know, tertiary alkyl halides do not undergo substitution reactions by SN2 mechanism due to steric hindrance at the backside of alpha carbon. What does this mean? Does it mean that tertiary alkyl halides do not undergo nucleophilic substitution reactions? They do, but by another mechanism, which is SN1 mechanism. SN1 mechanism is a unimolecular mechanism in which the rate of the reaction depends only on one species. If we look into the mechanism, what we find that SN1 reaction is a multi-step process. The first step is the slow ionization step, which involves the cleavage of bond between the carbon and the leaving group, resulting in the formation of carbocation. This is a slow step. The second step is a fast reaction in which the nucleophile attacks the carbocation, resulting in the formation of the product. The carbocation is strong electrophile and reacts very fast even with weak nucleophiles, which may be solvent molecules. The formation of carbocation is the slow or a rate determining step. And the subsequent step, that is the formation of the bond between the nucleophile and the carbocation, occurs very rapidly because the slow step of the reaction involves only the substrate. This reaction is unimolecular. Since the rate of the reaction does not depend on the concentration of the nucleophile, we can conclude that nucleophile is not present in the transition state of the rate limiting step, and the nucleophile must react after the slow step. That is, bond breaking between the carbon and the leaving group is entirely completed before bond formation with the nucleophile begins. The mechanism is hence designated as SN1, where S is equal to substitution, N is equal to nucleophilic, and 1 indicates that the reaction is unimolecular, that is, only one species is involved in rate determining step. So the rate law of SN1 reaction is that the rate of reaction depends only on the concentration of the substrate, in this case an alkyl halide, and not on the nucleophile. So the rate equation becomes rate is equal to rate constant into the concentration of the alkyl halide. This rate equation is first order overall, that is, it is first order in the concentration of alkyl halide and 0th order in the concentration of the nucleophile. As you can see on your screens, when we conduct a reaction of a tertiary butyl bromide with water, and in this reaction, if the concentration of the alkyl halide is doubled, the rate of reaction also doubles. That means the reaction is first order when we consider the concentration of the substrate. Whereas when we double the concentration of the nucleophile, there is no effect on the rate of the reaction. That means the rate of reaction depends only on the concentration of the substrate. Let us discuss this mechanism by taking an example of reaction of tertiary butyl bromide with sodium iodide. This is a rapid reaction in which tertiary butyl iodide is formed. As I've already said, that SN1 reaction proceeds in 2 steps. In the first step, as you can see again on your slides, that since the bromine atom is more electronegative than carbon, it pulls the bonding pair of electrons towards itself, as a result of which this bond becomes weak and bromine departs as a bromide ion, resulting in the formation of a tertiary carbocation. This reaction is a slow step because this is an endothermic reaction which involves bond cleavage only. This reaction is facilitated by the solvent molecules here, whereas they do not take part in the reaction. In the second step, the carbocation reacts with the nucleophile, and this step is a rapid step. Since this is an exothermic step, only the bond formation is taking place here, resulting in the formation of tertiary iodobutane. Let us take another example where tertiary butyl bromide is treated with water. Here water is a weak nucleophile, and in this reaction, water acts as a solvent as well as a nucleophile. Because this reaction takes place with the solvent acting as the nucleophile, this reaction is called as solvolysis. Solvo for solvent and lysis meaning cleavage. So as you can see on your screens, I have shown the reaction of a tertiary butyl bromide with water, resulting in the formation of tertiary butyl alcohol, hydronium ion, and a bromide ion. The first 2 steps are similar to the reaction mechanism which we discussed for reaction of tertiary butyl bromide with sodium iodide. That is, the first step is the slow step where the leaving group departs as a bromine ion, resulting in the formation of a tertiary butyl cation. In the second step, which is the fast step, the tertiary butyl cation reacts rapidly with water to form tertiary butyl oxonium ion. This completes the nucleophilic stage of the mechanism. That means it involves the nucleophilic mechanism involves 2 steps. First step is the formation of the carbocation, which is the slow step, and the second step is the fast step, which results in the formation of the tertiary butyl oxonium ion. Since the nucleophile is an uncharged molecule like water, the positively charged product must lose a proton to give the final uncharged product. So in the next step, which is again a fast acid-base reaction and which follows the nucleophilic substitution reaction, results in the formation of the tertiary butyl alcohol. In this reaction, solvent molecule acts as a base, and in this, tertiary butyl oxonium ion reacts with the water molecule, which is acting as a base through lone pair of electrons on oxygen, and it abstracts a proton from tertiary butyl oxonium ion, resulting in the formation of tertiary butyl alcohol, and a hydronium ion is formed as the side product. So let us look into the energy diagram of this reaction. What is an energy diagram? It depicts the change in energy in the system during the progress of the reaction. As you can see on your screens, on the x-axis, we have taken the progress of the reaction, whereas on the y-axis, we have taken the change in the energy during the course of the reaction. As you know, this reaction is taking place between tertiary butyl bromide and water. And we know that this reaction is a unimolecular reaction. So in this first part of the reaction, only the alkyl halide, that is the tertiary butyl bromide, takes part in the reaction. As we can see, we are going uphill in this reaction. That is, this step is an endothermic step in which there is bond cleavage between the carbon and the leaving group. So slowly the energy of the reaction is increased till we reach a maximum, which is the first transition state. In this case, we observe that there is partial bond between the carbon and the bromine atom. That is, there is charge separation. That is, carbon has a partial positive charge on it and bromine has a partial negative charge on it. So this is the most critical stage of the reaction in which bromine can leave as an bromide ion, or it can stay in bond formation with the carbon atom. And this step is also the most critical step, that is the formation of the carbocation is most critical, because this is where we have to cross a great energy barrier to convert the tertiary butyl bromide into a carbocation. After we've reached the transition state, the bromide ion starts leaving, and this is stabilized by the water molecules. That is, here the water molecules do not take part in the reaction. They only stabilize the ions being formed by solvation effect. Hence, the energy of the reaction starts decreasing, that it starts going downhill, and in the valley we get an intermediate, which is a tertiary butyl carbocation. This tertiary butyl carbocation is less stable as compared to the starting compound, because in this the central atom has a positive charge and is attached to 3 alkyl groups by fully formed bonds. And on the other hand, this is more stable as compared to the transition state, in which there is partial bond formation or partial bond formation or cleavage between the carbon and the bromine atom. In this step, carbocation is an intermediate which can be isolated, whereas we know that the transition state is highly unstable and it cannot be isolated. So this step is the slow step, because this is the energy requiring step in which there is bond cleavage between the carbon and the leaving group. Now, at the second stage, the water molecule acts as a nucleophile and very quickly reacts with the tertiary carbocation, resulting in the formation of the second transition state. In second transition state, the bond formation is taking place between the carbon and the oxygen, and there is partial bond between carbon and oxygen, and this bond is stronger than the bond of in that between carbon and bromine in the first transition state. So second transition state is more stable than the first transition state, and it is at the lower energy level. That is, activation energy of the second step is lower than the activation energy of the first step. Now the bond formation proceeds further, that is between the carbon and the oxygen atom, resulting in the formation of tertiary butyl oxonium ion, which I have not shown here. This tertiary butyl oxonium ion then reacts with water molecule, and the water, acting as a base, abstracts a proton from the tertiary butyl oxonium ion, resulting in the formation of tertiary butyl alcohol. Let us look into this graph again. So we can say that the position of the carbocation is like a mountain valley. That is, it is occurring in between the reactant and the product. That is, its energy is higher when compared to reactant as well as the product. Whereas, when we compare its energy to the transition states, then its energy is lower than both the transition states. And now if we look into the activation energies, then we find that the activation energy of the step 1 is high. It is directly related to the rate of the reaction. That is, since we require more energy to go uphill or to break this bond, that means we need a greater effort and the reaction will be slow. Hence, if the energy, the whole of the reaction, the rate of the reaction will depend on this slow step. I can take an analogy here where we say that if we are regulating, if we look at the movement of the traffic on a highway, we say that this movement will depend on how efficiently the traffic inspector gives clearance to the vehicles at the checkpoint. This is the slow point step. That is, how efficiently will the alkyl halide cross the energy barrier, that is the transition state. And once this vehicles have crossed this point, the movement will become fast. So what I mean here is, once the bond cleavage has taken place between the carbon and the leaving group, resulting in the formation of the carbocation, the reaction will be fast. So that means the rate of reaction does not depend on the second step. In totality, it is the first step which really determines the rate of the reaction. Let us now discuss the stereochemistry of SN1 reaction. SN1 reactions are not stereospecific in nature, since carbocation is formed as an intermediate. To illustrate this point, let us discuss the solvolysis of a chiral compound, that is S3-bromo-2,3-dimethylpentane in ethanol, which results in the formation of a racemic mixture. The carbocation, which is formed as an intermediate in this reaction, is planar. Hence, nucleophile can attack from the either face, giving both enantiomers of the product. The product is either racemic or at least less optically active than the starting compound. When I say less optically active, what I mean here is that it is less optically pure. That is, it will not be only the one enantiomer, whereas it will be a mixture of both the products, that is the R and the S enantiomers. So if the nucleophile attacks the carbocation from the front side, that is the side the leaving group is departing, the product molecules show retention of configuration. Whereas attack from the backside gives a product molecule showing inversion of configuration. Racemization is thus simply a combination of these two events, that is, retention and inversion. Look at this at your screens. Here we've taken 3-bromo 2,3-dimethyl pentane as the substrate. The first step, which is the slow step, results in the formation of the carbocation. As you can see, the structure of the carbocation is planar, in which the central carbon with its 3 bonds to the alkyl group is planar, whereas the unhybridized p orbital is perpendicular to this plane. So that means that now the nucleophile can attack the carbocation from its either face. It can attack from the front face, that is from the side from where the bromide ion is departing, resulting in the formation of S structure where there is retention of configuration. Whereas if it attacks from the opposite side from where the bromide ion is departing, then there is inversion in configuration. And this planar carbocation is optically inactive, or it is achiral, and it results in the formation of two products in which one is having retention of configuration, whereas in other we get a product where there is inversion in configuration at the chiral carbon. Now, when the racemization occurs, the product is rarely completely racemic. Why is it so? Because there the inversion is often more than retention. And in this case also, we get 40% product in which the configuration has been retained, that is the S product, whereas the 60% is the one in which we get the inverted product. Why is it so? This is because as the leaving group departs, it partially blocks the front side of the carbocation. That is, there is repulsion between the negative charge on the bromide ion and the lone pair of electrons on the oxygen, and this approach is hindered. Whereas the backside approach is unhindered, so the attack is more likely to be there. Let us take another example of a cyclic compound, that is reaction of cis-1-bromo 3-deuteriocyclopentane with methanol. Here again, the nucleophile can attack the either face of carbocation, but the attack will be more from the backside. As I've already said, as the leaving group, that is bromide, will partially block the front side as it leaves. Hence, the backside attack, that is the inversion of the configuration, is slightly favored. So in the first step, the bromide ion departs, resulting in the formation of the carbocation. And this hungry, empty, unhybridized p orbital of the carbocation now reacts with the nucleophile. The nucleophile attacks the front face of the carbocation, but here this side is slightly blocked due to the presence of the leaving group. The leaving group has not completely departed, and this will give us a product in which there is only 40% of retention of configuration. Whereas when we look into the backside attack, there the attack is unhindered and we get a 60% product in which there is inversion in configuration. So what we observe here is that when we are starting with the cis product, that is in this case, the deuterium and bromine are on the same side, and because of the front side attack, we again get a cis product in which the methoxy group and the deuterium are on the same side. So in this case, I have not taken the reaction with water, whereas we have shown you the reaction with methanol. And in this case, we are getting a cyclic ether, in which, in the first case, there is 40% retention of configuration. That is, we are getting a cis product. Whereas, in the second product, we are getting a trans product, in which the inverted product formed is 60%, because the attack from the backside was unhindered. When I started with this part of the reaction, I had said that we are conducting the reaction of the substrate with water. So if we conduct the reaction of the substrate with water, we will get an alcohol, which will be a racemic mixture. And when we conduct the reaction with methanol, we are getting an ether, in which we are getting a mixture of 40% retention product and 60% inverted products. So if now I highlight the conditions or highlight the points of an SN1 reaction, we can conclude that SN1 reaction takes place in two steps. The first step, which is the rate determining step, is the slow step and is an endothermic reaction which results in the formation of a carbocation. Second step is a fast step in which the carbocation reacts with the nucleophile, resulting in the formation of product. And this reaction is a fast reaction since it is an exothermic reaction. It is the slow step, which is the first step, which determines the rate of the reaction. Since carbocation is being formed as an intermediate in this reaction is accompanied by racemization, since the nucleophile can attack from the either side of the sp2 hybridized carbocation. Thank you.